So, we are part of the way through section 2, chapter 1. So that's where we're going to start today, finishing that up. Let's see, where do we make it to? Oh, we had the rich uncle. I had the rich uncle, so that was where we ended up. Okay, remember this section, we're just using general problem-solving strategies. And on that one, we found a pattern. We figured out we were going to be rich by the time we were 18, so that was nice. Okay. Good thing to know there. Okay. So let's see what's next. Anybody had any trouble getting registered for Hawks or anything? Most of us are on there. We've got a couple stragglers, but okay. Yeah, so if you run into any trouble on that, just let me know. Okay. So let's look at our next problem. This one says a baseball league is forming in which each of the teams will play 4 games against each of the other teams. We've got 5 teams in the league: Raiders, Jackals, Blazers, Warriors, and Eagles. And we want to determine how many total games will be played. So this is one, if we just try to count it up, it gets confusing. So let's make sure we've got our key information, okay? It says each team's playing 4 games against each of the other teams. And we've got 5 teams. Here, you may be able to come up with a way to just calculate it, but that's probably more trouble than it's worth. So our suggested strategy here, and I think it's a pretty good one here, is to draw a diagram. You may be able to think of a way to make a list or something like that and use that strategy instead. I think the diagram works pretty well here. Okay. And luckily for us, when we're trying to label our diagram, we've got our 5 teams, and they all start with a different letter. They set us up well there, so that's going to help us. Okay. Okay. So you may be able to think of a different way to sketch it out, but this is how I'm going to draw it. Okay? You don't have to do yours exactly like this. What I would do is, I know we've got the 5 teams, so I'm just going to label them. And I'm just going to use the first letter of each team. Oh, yeah, it's an ugly W. Okay. There's our 5 teams. And then one thing that kind of can help us on this one is, I didn't get that very symmetric, did I? That's kind of lopsided. It's okay. One thing that can kind of help us on this one is we know that each team's playing each one of the other teams 4 times. That was what it told us. So to keep it from being so messy, instead of drawing like 4 arrows between all of them, we can just do 1 arrow, and we just have to remember that 1 arrow means 4 games. Okay? So that can help. Okay? So my idea here, what I'm doing is I'm going to draw a line between 2 teams that play each other, and then we can just count how many lines we end up with at the end. Okay? Like the Raiders, we know they have to play the Jackals and the Blazers and the Warriors, well, the Eagles. And the Eagles. Okay. And since I can, I guess I'll go ahead and switch colors. It'll make it a little bit easier there. Then we want to just go to one of the other teams. It doesn't matter which one you do next. I guess I'll just go clockwise. We'll do the Jackals next. So we've already got the games between the Raiders and the Jackals, so we don't have to draw that one in again. Okay. We just need to get the other one. So we got to do the Jackals and the Eagles, Jackals and the Warriors, Jackals and the Blazers. Oh, yes, sheet, okay. All right, so then I'm gonna go to the Blazers, but this time it's getting easier. This time I've already got the Blazers and Raiders. I've already got the Blazers and the Jackals, so I've just got to draw in 2 more lines, right? So, let's see what other color I've got here. I need the Blazers and the Warriors, and the Blazers and the Eagles. Okay.
What about Eagles and Warriors?
Oh, we're not done yet. Yeah, you're right. Okay, so Warriors, I've already got them in the Blazers, them in the Jackals, them in the Raiders. So the only one we're missing is Eagles and Warriors. For the Warriors, so we can fill that one in. Okay, we'll do some color over here. Okay, and then come in. And then we started with the Raiders. Started with the Raiders. So we're down to the last one with the Eagles, but we don't have to draw anything in on it because we've already got all the other games drawn in. We've got E to R, E to J, E to B, E to W, so good on all those. So what's left to do to solve our problem? Count the lines, and then what do we have to remember about the lines? They're all 4. That's good. They're all 4 games. So let's see. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines in there. We've got to remember each line is 4 games. We had 10 lines. So how many total games? 40. We'll play 40 total games. And that might seem like a little bit of overkill there, but if you start trying to count, it gets confusing and you forget, well, I don't have to count this one twice and things like that. So diagram's pretty helpful there. Questions on that one? Not too bad. Okay. Let's see what's next. I think we just have a couple left in this section. Okay. Well, what did it do? Let's look at this one. This one says, how many ways can you make change for 50 cents out of quarters, dimes, or nickels? Or what it means when it says or here, or any combination. Can you think of any ways we can do that? Go on.
You could separate all like the quarters and the nickel like a T-chart or something.
Yeah.
Anytime you goes into 50 cents and then.
Yeah. I think that's a good idea. So in our suggestions, make a list. So I think that's a good way to do this one. So if you start just trying to think through all of them, it won't take you long before you realize it's probably too many to keep track of without being a little organized. So if nothing else, we'll use our list to keep us organized. Okay, so the idea we heard there is I'm going to make it easy on myself. I'm going to make 3 columns. I'm going to do Q, D, and N for quarters, dimes, and nickels. Okay. And then to be kind of organized, I'm going to try and do the biggest coins I can to start with, the biggest, highest value coins first, and then work our way down from there. Okay? So another way you can think about that is I'm going to try and think about it from the least number of coins I would have to use to the most number of coins. So what's the easiest way to make change for 50 cents there? 2 quarters, yeah, 2 quarters. So we'd have 2 quarters and no dimes and no nickels. That would work. 1 quarter. 2 dimes and 1 nickel. That'll also work. Huh?
1 dime. 3 nickels.
Yep. Yep, that's good. And then I ran out of room, so I'm just gonna make another little arc. All right, so yeah, we can't use quarters anymore, if you think about it. 5 dimes, 0 nickels. 5 dimes is 50 cents. And then instead of 1 of the dimes, we could do 2 nickels. And then we can kind of do the same thing. We can change another dime to 2 nickels. And I should have written smaller. Okay. And then I got to squeeze in 1 more. What's the last one going to be? 10 nickels, yeah, 10 nickels. So, sorry, I wrote too big. 0 quarters, 0 dimes, and then 10 nickels. Let's see. Oh, sorry. And you can kind of tell if you're organized about it, you can kind of tell that that's all of the possibilities because we were kind of systematic, right? We said, well, we can change a quarter into 2 dimes and a nickel, or 1 dime and 3 nickels, or all nickels. We could do the same thing with another quarter, right? Change it to all dimes, go through there. And check over it. Remember, that's one of our steps. We want to check and make sure our solution makes sense. And make sure we don't think we missed anything. Luckily, they didn't ask us to use pennies. Because if we had the option of pennies, we would need some more slides. Okay? Because, you know, especially you get down to the end, every time you change a nickel, you get rid of a nickel and do 5 pennies, get rid of another nickel, do 5 more pennies. Be a lot more. Questions on that one? No? Okay. 1 more here in the slides, and then I had a question about 1 on Hawks we'll talk about. Help you out on that one. Okay. All right, so this is more like a classic algebra class math problem. I'm sorry, we won't do a lot of algebra in here, but that is part of problem solving. Okay. This says a number is multiplied by 8, and the product is added to 6. If the sum is 30, what's the number? So you may be able to just reason your way through this, okay, but if not, using a variable is a good way to do this problem. That's why we use variables so much in algebra, is they work really well for things like this. So our variable is just going to be this some number or a number, and we can pick whatever variable we want to use. So what variable? X. Okay, I'm fine with that. That's a classic thing. We can use X. So then we just want to change this from words into math symbols. Okay. So it says a number is multiplied by 8. So times 8. If you want to, you can go ahead and write that 8x if you're comfortable with that. But I'm just kind of going in the order they say it here. And that product is added to 6. Okay. And it says the sum, when we get finished adding that, is 30. So that means this thing on the left equals 30. And if you want to write it the way you're used to seeing it in algebra class, that's okay. You can just say 8x plus 6 equals 30. We won't have to do much of this in here, but you remember what to do to figure out what x is on this one? So yeah, we'll subtract 6 from both sides because we want to get rid of that. That gives us 8x equals 24. And so to undo, we're doing 8 times x, so to undo that we divide by 8 on both sides. And then, yeah, 24 divided by 8 is 3. And then if we're following our problem solving process, we need to check it. Okay, so if we take 3, we'll call it 3 instead of x this time, and multiply that by 8, that gives us 24. And then we add that to 6, and that does give us 30. And 24 plus 6 is 30. Okay. We'll try to shy away from all the algebra we can, but sometimes it is helpful. Okay. That's kind of the point of, part of the point of having to learn some of the basic algebra at least. Any questions on that one? Was that like the one you asked about, or is that different? It was a little bit different, okay. Yeah, all right, so there is one that's can be a little confusing that's similar, where it's probably helpful to use a variable in Hawks. Let's pull one of those up. Okay. Internet's been a little slow in here. Been really slow. Okay. So let's see, 1, 2. I'm just gonna skip until we get to the one we're looking for. Yeah, it's like it, isn't it? That's tiny. Let me zoom in. Okay. Is it in? All right, so this one's just got really one more step in there. The first part starts off like the one we just did. It says the number is multiplied by 15, and then we take that answer and add it to 5. But the other little thing it gives you that makes it a little bit trickier, it tells you that it doesn't just say the sum is equal to some number. On this one, it says the sum is equal to the product of 5 and 7. Okay. So we can almost set it up the same way. Okay. So we've got a number multiplied by 15. Let me get some scratch paper here. So I got a number multiplied by 15. So I'm just going to go with x again. You don't have to use x. If x gives you anxiety, you pick some other variable, okay? That says we've got some number that's multiplied by 15. I'm going to go ahead and write it kind of traditional way. And then it says we take that and add that product to 5, so plus 5. And then it says that sum, okay, that thing we get, is equal to the product of 5 and 7, so that means it's equal to 5 times 7. Really, we're just adding in one more step over there. We've got to do the 5 times 7 part. That's 35. And then it's just the same steps as we used before. We subtract 5 from both sides. And then last step, what we do? Divide by 15. So 30 divided by 15, that's 2. Okay. Yep. Was it different? Let's see. Oh, yeah, it was a different one. Okay, well, we got one more to do, sorry. You'll be ready for that one, though. Yeah, okay, here we go. So this one says the product of two whole numbers, that just means no fractions, no negative numbers, is 825, and their sum is 58. What are the two numbers? This is one that's really tempting, especially if you've been taking algebra as your last couple of math classes. Really tempting to sit down and try to find the formula. And like that's kind of how you've been trained. But we don't have to do that. We've got a bunch of other strategies we can use. So I think we can do better than trying to hash out a formula here. What other options do we have? Can you think of some other way to try to figure this out? What I would do is I would look at that part where it says their sum is 58. That means we've got two numbers, and if we add them together, we get 58. So I would just guess a couple of numbers that we can add together and get 58 and multiply them together and see if we can get 825. Okay, so let's try, see how long it takes us. It shouldn't, it depends on how good of a guesser you are. Okay. 825 is what we're trying to get. That's our goal. And our numbers need to add up to 58. Okay. So, what do you think? 825 is pretty big. So what I think when I look at that is I'm going to try and split my 58 up pretty evenly. It doesn't have to be right down the middle, but we're just looking for two numbers that add up to 58. That's easier than trying to come up with a formula, I think. So what can we do? Maybe 25, and if we take 25 away from 58, is it 29? You can check it with a calculator, is that right? No, that's right. Yeah. 50, no. My brain's not working all of a sudden. What did you get? 20, oh, okay, what's 29?
29 and 20.
29 and 29, yeah. Sorry. I need to get my calculator out too, apparently. Okay. Yeah, that's 29, that makes sense. Okay. Happens to everybody. Okay. Doesn't matter what PhD you go to down the hall. Okay, you just mess up sometimes. Okay. So then how do we check it? How do we see if those are our two numbers? Yeah, multiply them. So I am going to get my calculator out for that. So if we multiply these, we get 841. Well, that's not it, but it's kind of close. All right, so I'm not gonna do anything drastic like change to 57 and 1. I'm gonna stay kind of in the 20s, so I'm gonna adjust it just a little bit. Maybe we can try like 30 and 28. So this is just guessing, test or trial and error, right? We said that's a valid problem solving technique. That, oddly enough, gives me 840. So maybe we need to jump a little bit more. Maybe we can change them by 2. So maybe 32 and 26. Try that. That's 832. So we're going in the right direction. That's not taking too long. Try 34 and 28. Uh-oh. Anybody done 34 and 28? Yeah, it's too big. That gives us 952. I think. What'd you got? 25. My brain's not working. 25 and, okay, it's 58 minus 25, right? 33, okay. I can't hear well with everybody wearing masks, I'm sorry. Okay, so let's try that one then. 25 times 33 is 825. Is that what we were looking for? Yep. Okay, so I got kind of unlucky on guesses. I was kind of, I skipped over it. So it took a little bit longer than it could have. But we got there. And we didn't have to do any real fancy thinking. Right? Didn't have to stress our brain too hard. Right? Not too bad. Right? Okay with that one? Does it feel like you didn't accomplish anything just because you just guessed? That's just bad math history in your past. Okay, look, the hardest math problems in the world. I promise, you take the greatest mathematician, if they could somehow guess it and get it right, they would be real happy. So, nothing wrong with guessing and testing. Okay, nothing wrong with that at all. Right. Other questions on that section? Okay, well, we're done with chapter 1 then. Here, we might not make it all the way through 2.1, but that's okay. So we're kind of into our first, I guess you could say, normal chapter for how the material is laid out in this class. And because normally as we move to different chapter, we're kind of looking at a different branch of mathematics. So in chapter 2, we're looking at some stuff from a branch of mathematics called set theory. But it's not just people that work in set theory that use this stuff. We use the basic stuff in lots of fields. That's what we're looking at these things called sets. Okay. So we want to develop a basic understanding of set operations here, and before we can do that, we have to get our definition of what a set is and things like that. That's the kind of downside to covering so many topics. You have to take a little while when you start a new topic to kind of get familiar with the field, get familiar with that branch of mathematics there. So we have some vocabulary that comes at the beginning of every chapter. Okay, but why do we care about sets? Well, remember the main thing, okay, the big picture, I'm not going to mention this every time, but the big reason why we're studying this stuff is it grows our brain and makes us better thinkers, better problem solvers. Okay, but the actual applications of sets, there are applications of sets that we use just in life. Okay, you may not think about them specifically as mathematical sets, but you're using them. Anybody ever organized their closet before? Anything like, yeah, okay, well, you were putting stuff in sets. You just didn't think about it that way, probably. Okay, because all we're doing with sets is we're coming up with some system to group things together, basically. Okay. And we can do that several different ways. Okay. You know, not everybody's closet's organized the same, right? Some people have got stuff organized by color or season or different things like that, but those are all valid ways to do it. Okay, those are all different types of sets there. So we do stuff like that all the time. Some of us don't do it as much as we should, and maybe we're not quite as organized as we should be, but we do use that type of information. So, and kind of mentioned this already, but set theory is kind of a branch of math that you do have people, like you have people that that's what they do all day, right, as they research stuff about set theory. But we use set theory in a lot of different branches of math too. So it's not exclusive, okay, to those people that study that field. Okay, so in math class, what do we mean by a set? Okay, you can have an idea of what we mean by set in just English. But usually we're being pretty specific when we define something in math class, so, or in math, not just in class. Okay. So what's a set? Okay. But it's pretty generic, okay? Very general, maybe a better sounding way to say that. A set's just a collection of objects. So here we're dealing with stuff that's not necessarily numbers. And then each one of those objects in a set we call an element or a member of the set. So that might be something you want to take note of. And that's it, very general. So you can have a set of kitty cats or you can have a set of irrational numbers. Okay, you don't have to be thinking about normal math class stuff, really, what you're used to with sets. And the next thing to talk about is how we write down the set. Okay, we actually have two ways that we do that. The first way we're going to look at is called the roster method. So what's a roster? It lists, yeah, it's just a list of list of names or just a list. So like the class attendance sheet, that's like our class roster. Just listing things out. So that's all roster notation is as well. As we list out all the members of our set. So we list them out. And you can think about it kind of like grammar for math. Okay? The notation that we use generally when we're naming and listing out a set, we usually give sets a name that's a capital letter, uppercase letter. Okay? And then when we're listing out our set in roster notation, we'll have an equal sign. And then we have the curly brackets. Okay? And then each thing that's in the set, we separate with a comma. Okay, so like this, we would call this set A. And the elements or the members of set A are 1, 2, X, Y, and Z. That's what this says. And those are just listed out, so that's roster method. Okay. All right, so if you see that, you'll hopefully know what you're looking at there. Now, the next thing to talk about is equality. If we have two numbers, we know what it means for those two numbers to be equal. Like 2 equals 2. Okay, we can agree on that. Okay, and then we even get a little fancier with that in algebra. We'll say some unknown quantity plus this equals some other number. But what we want to think about the same idea for sets. Okay. If we have two sets, we say the two sets are equal if they have exactly the same elements and exactly the same members. Okay. Now, if you're thinking about the sets being listed down, the order that they're listed doesn't matter. Okay. It just matters that the things in the sets are the same. And then if we have two sets and we want to say they're equal, we just put the normal equal sign between them. So nothing too special there. Another thing we talk about sometimes with sets is how many elements, how many members there are in a set. So sometimes we want to say like one set's bigger than another set, so we want to be able to talk about how many members each set has in it. So we have a formal name for that. Okay. That's called the cardinal number, or the cardinality of a set. Okay. So it may not be a familiar term to you, but all that means is how many members are in the set. How many things does the set have in it? And our notation for that, it looks like, it looks weird up here because we don't have a set name in there, but it just looks like the absolute value symbol. You remember what absolute value looks like? Just the two vertical bars on each side. That's all that is there, even though it looks strange because it's empty. But, so if we have this set A, I can't draw a curly bracket today, let's see. Yep. And we'll say it has the letters A, B, C in there. And if I want to talk about the size of that set, I could say the cardinal number or the cardinality of set A. So it looks like the absolute value of A. And what would that be? How many members do we have in A? We got 3. Yeah, we got 3 in there, right? Yep, 3, A, B, and C. Yep. A, B, and C. And then what if we had a different set? Just picking random letters now. What would the cardinal number of set B equal? That one's still 3. Yeah. So it doesn't matter what's in there. It's just how many of them do you have? Okay. How many of them do you have? Okay. But if we go back to our last vocabulary term, if I asked you, well, let me just write it down. Okay. I asked you, does set A equal set B? No, why not? That's right. So these two sets are not equal, okay, because they don't have exactly the same members. They don't have exactly the same objects in them. Okay? B's in both of them, right? But A's not in this one, C's not in this one, G's not in that one, H is not in that one. So since they're not exactly the same elements, those two would not be equal at different elements. Okay. Let's look at an example here. This one always, you have to help me. And says use the roster method to represent S, the set of states in the United States that begin with the letter M. Okay. So that's our first thing. I can do this part. I can say set S equals, and then curly bracket, and then we need the states that start with the letter M. Single one? Oh man, you had to start with Massachusetts. I'm gonna abbreviate. Okay, Massachusetts, Maine, Michigan, Maryland, yeah. Montana, and I'm running out of room, so I'm gonna go down to the next line. Is that all? We've got a neighbor here pretty close by. Yeah, Mississippi. And then what about spelling that one? Yeah, yeah. So you didn't go crooked letter, but you had a good rhythm though. I liked it. So the old things: M-I, crooked letter, crooked letter, crooked letter, crooked letter, humpback, humpback. So. Missouri. Yeah. Think of any more? I can't remember how many there are.
Like 8.
Minnesota, yeah. And it? Amen. Okay. I'm pretty satisfied with that. Do you think that's? May I think of another one? Just 8. Okay. We got 8. Yeah, we got 8. Okay, good. All right. So we kind of answered the next part, right? What does that absolute value of S thing mean? How many we got in there, right? So we could say the cardinal number is 8. Yeah. Yeah. Yep. Hey, you didn't know you were going to have to do geography today, did you? Okay. All right, one more idea, and then this will be our last thing today. It'll be a good stopping place. Okay, one more idea. On the last two, we said these were not equal because they did not have the same members, right? But what about their cardinal numbers? They were the same. Right? So that might be something we want to be interested in, right? Are they the same size? And so they can be not equal, right? But we might want to know if two sets are the same size, even though they're not equal. So one more term here. Okay. What we call equivalent sets. It's a little tricky. You have to keep straight the difference between equal and equivalent. Okay. We say two sets are equivalent if they have the same cardinal number and if they're the same size. And then our notation for that's a little maybe unfamiliar to you. It's just a little squiggle. Okay? So it's just squiggle. Okay. You may know the name for that symbol.
Approximately? Well, no,
Well,
that's,
you can use it to represent approximately, yeah. See, if you actually stop and think about the names of the symbols we use, that's like, I don't know, a weird hobby of mine, I guess, is thinking about the names of the weird symbols we use we never talk about. But that one's on the keyboard. It's, I do not remember how to spell it, but it's tilde or tilde. Just a little squiggle. Okay, so it means two sets are equivalent, which means they have the same number of elements. Okay. Okay. I just say squiggle. I don't say tilde. Okay. All right, so let's think our way through this last example, and then we'll stop here for today. Okay. Now we've got a couple of pairs of sets, and we want to know if the sets are equal, or are they equivalent, or neither. So on example A, we have set A has public health, international studies, mechanical engineering, music education, political science, so maybe college majors in there. And then B has Tim, Gloria, Alan, Warren, and Karen. So first of all, would those sets be equal? Yeah, they would have to have the same elements to be equal. So on A, they're not equal. Are they equivalent? I haven't counted yet. So to be, oh, they're not. Okay, so to be equivalent, they would have to have the same number of elements, but the first one has 3, 4. Yeah, they're both 5. Okay, they're both 5. Yeah, you have to be careful where the commas are on that because it kind of split up. So yeah, so they both have 5 elements. So they are equivalent. And if we want to be extra special here, we can say the cardinal number of both of these is 5. Okay. And then what about example B? Are those equal?
yes.
They are. What's the difference between the two? They're just reversal order, but the order doesn't matter on that. Order doesn't matter as long as they have the same elements in there. So X does equal Y. Are the two sets equivalent? Yes, they are, because they also have the same number of elements. So one thing to point out, and then we're done. Two sets can not be equal, but they are equivalent. But if you have two sets that are equal, that have the exact same elements, that means they also have to be equivalent, because that'll mean they have the same number. And so if you know they're equal, you also know they're equivalent. That's not true the other way around. Okay? All right, if you didn't get it on the sign-in sheet, we'll put it up here at the front. If you need to get it on the way out, is it? Thank you. I'll put it up here, and then other than that, I will see you on Friday.